In today's tutorial we will discuss mechanistic details of the so-called Reimer-Thiemann reaction. A phenol as substrate reacts in the presence of chloroform and an excess of potassium hydroxide, finally to give salicylic aldehyde, of course after protonation. This is not a very good reaction since the yields are at maximum at about 50%. However, it is remarkable ortho selective. So, we can be sure that under the basic reaction conditions, the phenol, the acidic phenol, will be deprotonated. So we have the potassium phenolate as one reactive component, and from the preceding tutorial we already know that chloroform in the presence of potassium hydroxide will undergo an alpha elimination to give the highly reactive dichlorocarbene. This is electrophilic, this is nucleophilic, and a CC bond formation might take place. Under dearomatization, deprotonating here, protonating there will lead us to the again aromatized potassium phenolate, now with a dichloromethyl group here in this position. This carbon has the same oxidation state as here in the aldehyde. That means that just an hydrolysis of this group will give us that carbonyl compound. How could the hydrolysis proceed mechanistically? If we eliminate potassium chloride, then we have an orthoquinonoid compound which will easily react with potassium hydroxide. This is the electrophilic center, the OH group. The hydroxide is the nucleophile. And now another equivalent of potassium hydroxide will eliminate HCl and the final aldehyde functionality is already generated. Just acidifying, and we are at the stage of our final product. Nice mechanistic scheme, however, it does unfortunately not explain the orthoselectivity. If you look up the mechanism that is explained, for instance, on Wikipedia, there you can read that this highly electrophilic species will prefer to be located close to the anionic charge. However, if it is already closely located to the anionic charge, why shouldn't that react directly with the center of highest electron density, and this is the oxygen? Let us have a look what structures we have if that carbon will directly react with that oxygen. So let's have a try. So, this would be the intermediate, and now an alpha elimination, as we know it, can take place. Potassium chloride is eliminated, giving rise to this carbene that has a phenolate and a chloride substituent. Such carbenes are known that they are so reactive that they can make an insertion reaction, for instance, into a CH bond, especially intramolecularly. And in the ortho position, we have CH groups. Insertion reaction means that, in this case, a four-membered ring would be formed which could easily break apart forming this orthoquinonoid structure, and hey, have a look, it's the same as here. So, this is an alternative reaction pathway I would like to suggest, which explains why the orthoselectivity occurs. Next step, of course, would be to think about how can one prove that experimentally. Thanks for listening.